Hello everyone, welcome to this tutorial. My name is Emerson Ahrori. I'm a Google developer expert. In this tutorial, I'm going to show you how to calculate chlorophyll content in the water bodies using Sentinel-2 imagery. This tutorial is really useful for those of you who are interested to learn about the water quality monitoring using remote sensing data. At the end of this tutorial, you will be able to plot the target lake and show how the chlorophyll content varies from one date to another date. If you want to learn how to do this procedure from scratch, let's open a notebook in the Colab environment. Go to the colab.research.google.com. There you can make a new notebook like this and start programming. Programming in the Colab environment is really easy to do. Just you need to know some basics about the Python and Google Earth Engine. I'm gonna make a bridge between Earth Engine and Colab and show you how we can use the Earth Engine capabilities and Python together in the Colab environment. In the first step, we need to call the essential libraries. The essential libraries to deal with the Earth Engine, like GEE map and EEE. And also we need Xarray as XR. Remember to install the XEE, one of the newest libraries developed by the Google community, allowing us to combine Earth Engine image collection and Xarray formats. Let's import the XEE. As it is not built-in available in the Colab environment, we have to install it first. Let's run the first cell, and then after all the libraries inserted, then we can install or we can establish a connection between Earth Engine and Colab environment. If you faced with any challenge in this tutorial, feel free to take my code. The code example is available below this video in the chat box on my YouTube channel, and also you can use it for your own project and you can share it in the social media. So once the installation done, then you need to clear the output. Make another cell. Now we need to use the EE library to establish the connection between Earth Engine and Colab. EE authenticate first, then initialize your Earth Engine account. The first argument is the project ID. If you go to the code editor environment, upper right, you will have access to your account information. Project info shows your cloud project ID. Copy and paste into the code. The next argument, OPTURL. If you search about the XEE library, you will find a GitHub address. As you can see here, there is a detailed instruction about the XEE and how to use it in the Earth Engine. If you scroll down a bit, the OPTURL already available here. Just select and paste it into the code. Let's run the cell. Now the Earth and the Colab asking us permission to have access to the Earth Engine account. Permission granted by clicking on Allow and clicking on Account Information or Account ID. There you go. So now connection established. From now on, we can use the Earth Engine capabilities, functions, and data catalog in the Colab environment under Python standard. Before further processing, we need to select the region of interest. Let's make a new variable, map. From GEE map, call the map function with the train base map. Let's run the map. As you can see, now we have a train map that you can easily browse and find your region of interest. In this study, I'm gonna select a water body, no matter where it is. This tutorial extendable to all around the world, not limited to only one single location. So, as you can see in the Iraq, there are some lakes available here. For example, I'm gonna use this one. It's a little bit bigger and also easily detectable by the satellite images. Through drawing tools available here, you can draw a rectangle that covers the lake, just like this. Now we need to have the rectangle as a variable. Make a new cell, ROI. From the map, select the last feature that is drawn. Convert it into a geometry. Let's run a ROI and the rectangle is available as a polygon. So, the next step is relevant to the satellite images. If you go to the Earth engine, through the search places and dataset here, just you need to write the Sentinel-2. As you can see, two kind of Sentinel-2 images available. The first is Sentinel-2 images. So let me open it up into a new page. The first one is the TOA product that is affected by the atmosphere. So this is not good for the spectral indices. Back to the code editor, the next or the second Sentinel-2, open it up into a new browser. As you can see, it's SR or surface reflectance. The surface reflectance means atmospherically corrected and the atmospheric impact removed from these images. The surface reflectance product is the best option for spectral indices. These dataset available with 5 days interval, so that's a good option for the water body monitoring. So first we need to copy the Earth Engine snippet to bring this dataset into the Colab environment. Let's make a copy and inside the new cell a new variable created. For example, the Sentinel-2, make a tuple then, just like this. Then we need to define a filter bounds and filter dates. Filter dates, I need to actually calculate the water chlorophyll for 2024. One single year, consider it here, 2004 to 2025. The 25 not included, only 24 considered. That filter bounds, the region of interest, the ROI. I need those Sentinel-2 images available for 2024 and the region of interest. So let's run the Sentinel-2 and see how many datasets available through the time. As you can see, 150 elements available in this period of time, but some of the pixels might be cloudy and we need to get rid of the clouds or mask them from the analysis. Back to the code editor environment, close the window, and here you can see the Sentinel-2 cloud probability is available. If you write the Sentinel-2 like this, you can see all relevant Sentinel-2 datasets. The Sentinel-2 cloud probability already actually showed us how much cloud cover available, how much pixels affected by the cloud cover. So there is a probability band in this dataset that shows the probability that a pixel is cloudy and the resolution is 10 meter and also well matched for with Sentinel-2 images. We can add the probability band to this image collection for 2024. It's really easy to do. That link collection is the function that helps us to do this. So the link collection has or receives two arguments. The first is the collection ID for the second collection, and the next argument is the band name. that is probability, just like this. Okay, let's run. When you run this data set, for each date, for 150 images, in every data, we will have Sentinel-2 bands plus the probability band. If you drop down the menu here, we have the features, go to the bands. In addition to the existing bands, probability bands added that help us to detect the cloudy pixels. So now I need to calculate the chlorophyll index, but I need to do some multi-step analysis first. In the first step, we need to get rid of the cloud cover using the probability band, and then we need to detect the water body, and then we can calculate the chlorophyll index. It's very easy to do in the ERS engine. So let's make a new function. For example, the function name is Sent2Q, Sentinel-2 quality, or Sentinel-2 water quality, or something like that. You can set any other name. So there is one input in the function, and that is Sentinel-2 images and probability band for each date. So cloud band sets to, from input image, select the probability band. Let me do a copy paste to make sure there is no typo here. So now I'm gonna make a cloud mask, or I'm gonna select the clear pixels, clear pixels here, for example, consider it as pixels in which cloud probability is less than, for example, 20. The pixels greater than 20 means the amount of the cloud cover is beyond the threshold that I have considered. So, and clear pixels already defined. So now I need to calculate the NDWI to separate the water body and non-water body. So NDWI sets to, but before the NDWI, we need to apply a scale factor. If you go to the data description for Sentinel-2, here you can see there is a scale factor that should be applied on our data set before calculations. The input images, all band starting with B, you can see the multispectral bands. First should be selected like this. Multiply them to the scale factor. This is the scale factor. Multiply to the scale factor. The bands now ready to use in the spectral indices. NDWI sets to get the bands and calculate the normalized difference between band green, band number 3, and near infrared, band number 8. If you go to the data description, you can see the band 3 labeled as green, band 8 labeled as near infrared. Their normalized relationship help us to identify the water body. So let's rename it as NDWI. So now I want to select the water body. From the NDWI, if you select the pixels greater than 0.1 showing the water body, and then we can have the water body separated from the other phenomena and land cover in the region. So now we have the clear pixels threshold and we have a water body now. In the next step, I need to calculate the chlorophyll index. There are various methods for water chlorophyll estimation, but here I'm going to use a reference based on a Sentinel Hub website. In the Sentinel Hub website, there are some empirical models for the water quality parameters. In this tutorial, I'm going to show you how to calculate the chlorophyll A. In the next tutorials, I will show you how to do the calculation for the rest of the indices. But in this tutorial, I'm going to show how to do this, the chlorophyll A. So a new variable should be created. This is, for example, CHL sets to, so, okay, get the bands because they are already processed and a scale factor applied on them. So that expression, we need to write an equation using the expression technique. So you can see here there is an equation that should be written in the Python based on the JavaScript structure in the description actually. 4.26 multiply, okay, make a tuple powers to 3.94, and here we have a division between band 3 and band 1, B3, B1. There is a division. So in the equation we have some known factors and some unknown factors. B3 and B1 are unknowns, and we need to actually define a real band. So now the first band number 1, from the bands select B1. Band number 3, from the bands select band number 3, just like that. The CHL is calculated. The output band name will be the CHL. The function finally return one output. The output here is the chlorophyll band or chlorophyll index that is updated based on clear pixels to get rid of the cloudy pixels, and it is updated based on water body to get rid of the rest of the pixels, non-water pixels. Remember that to copy the properties for the new output from the input image, only system time start considered here. We need the system time start because we need to do some spectral, some time series analysis in the next step. So now the function is ready. We need to apply the function on Sentinel-2 image. That map, it's a loop structure. Sentinel-2 quality or Sentinel-2 water quality. Let's run. After a few moments, we will have only chlorophyll band or chlorophyll image in each date. Drop down the menu, CHL is calculated, and system time start is also available. As you can see, here we have an image collection structure. You can see how it looks like. Now I'm gonna use the XEE and XR library to convert an image collection into multidimensional array structure. So make a new cell and variable name is XR. The variable name is DS. So from XR call open datasets. The input collection is Sentinel-2. The engine protocol EE, coordinate system EPSG 4326. This is WGS84 coordinate system that is unique in all around the world. So the scale means pixel size. The pixel size is based on a degree. 1 degree 100 kilometer roughly. So 0.1 10 kilometer. I prefer 100 meter as a resolution for this application. It is true that a spatial resolution ranges from 10 to 60 meter, but I prefer 100 meter resolution because not too much detail considered in this tutorial. So it's totally up to you whether you get the 10 meter, 20 meter or 100 meter resolution, because sometimes it's doesn't necessary to have the 10 meter, and when you set the 10 meter resolution, that highly reduces the speed of processing, and there is not too much difference between 100 meter or 10 meter for most of the applications. So but when you reduce the resolution to 100 meter, the speed of processing highly increases and helps you to do the more complicated models on your data. So the geometry region of interest should be ROI. The dataset now is ready. If you run the dataset, you can see no longer image collection is available. Now we have a multi-dimensional array structure. We have different dimension. Instead of a band, there is a variable that is chlorophyll, that its value available through the time, longitude, and latitude. You can see the array of time, longitude, and latitude separately. So now I need to sort the data based on temporal variations, because most of the time after doing conversion from image collection into multidimensional array structure, maybe we face with some sort of disorder in the temporal dimension. So we can get rid of that by sorting the data by temporal dimension, just like this. And I realized that if you do a simple multiplication, like multiply to 1, it highly increases the speed of processing in the next step. Scientifically, the data hasn't changed here, but we will have a new data set separated from the original one. That's why the speed of processing in the next step will be higher. It's a kind of trick, and there is no scientific reason behind. Let's run the data set, and now we should wait maybe for a minute or a little bit more. It depends on size of the area and the spatial resolution or the pixel size. All of them actually may have effect on the speed of processing, but hopefully you can see it's done after 18 seconds. So now we have the data set, and now I want to convert it into the monthly format. For example, DS monthly. Get the data set first, resample it to the monthly format, just like this. And I want to calculate the average over the time. Let's run. The DS monthly, now including monthly chlorophyll content for the selected area. Let's do the visualization. Select the variable, make a plot. X-axis sets to the longitude, y-axis sets to the latitude, call axis sets to the time, call wrap sets to, for example, 6. I want to have a multi-temporal plot that shows, for example, a multi-temporal plot that shows actually the chlorophyll dynamic from one month to another month. I prefer to have at least 6 plots per row. And robust sets to true, and let's run. As you can see, it's calculated, but the range of the values actually is a little bit very high. So we can rearrange the values by, or we can actually increase a little bit quality by changing the operator. For example, instead of the mean, we can calculate the median. Now you can see the output quality is a little bit better when we change the statistical operator here. In the next step, you can see most of the values ranges, for example, from 0 to maybe 20 or 30. Just a few number of the pixels gets very high values. So we can actually change the minimum value for the visualization and the maximum value. That highly increases the quality of the visualization. So for example, I set minimum to 2 and maximum to 30, and then the color map could be, for example, rainbow. you can change the color style or color palettes. Let's run the cell again, and this time you can see the chlorophyll content dynamic in your area with a better visualization perspective. And even you can actually set some levels for the legend. For example, here I can define some levels. The levels could be, for example, 20 levels to actually use the discrete color instead of a stretched color for the visualization. It's totally up to you what kind of the options considered for the visualization purposes. So as you can see, the reddish areas, higher chlorophyll content, the bluish areas, lower chlorophyll content. So there we go. And even we can change the style of the visualization by set the contour F here. That help us actually to use a different visualization. Sometimes contour F make a little difference, but sometimes actually it's a kind of generalization. You can see the amount of the detail a little bit reduced, but it's still up to you which kind of the visualization style utilized, because it's completely optional. That could be defined by the users. So now let me show you how to get export from the plots. Before getting export, we need to call matplotlib. Import matplotlib.pyplot as plt. The matplotlib is the main library for the visualization. So the plt.savefig, just like this. The figure name could be, for example, Sentinel-2 CHL PNG format. DPI should be 360 and BB box inches should be tight. Let's run. So if you go to the left panel, you will have a shortcut, Sentinel-2 chlorophyll. Select and download, just like this. Select a address and download into your system. Now here you have a high quality map that shows chlorophyll content dynamic in your study area. So you learned how to calculate the chlorophyll content for your region of interest using Sentinel-2 images. If you want to learn more, you can follow my YouTube channel. There you can find several tutorials about the Earth Engine data analysis. Thank you for your attention.